Shear force and bending moment diagrams are powerful graphical methods that every mechanical and civil engineer should know how to use to analyze a beam under loading. In this video, I'll explain exactly how to master these diagrams, and we will see how they can be used to understand how a beam is loaded. I want to start by explaining what shear forces and bending moments actually are. When a beam is loaded, internal forces develop within it to maintain equilibrium. These internal forces have two components. We have shear forces, oriented in the vertical direction, and we also have normal forces, which are oriented along the axis of the beam. If the beam is sagging, the top of the beam will get shorter, and so the normal forces in the top of the beam will be compressive. The bottom of the beam will get longer, and so the normal forces in the bottom of the beam will be tensile. Each of the tensile normal forces has a corresponding compressive force, which is equal in magnitude but opposite in direction. As such, these forces don't produce a net normal force, but they do produce a moment. This means we can conveniently represent the internal forces acting on the beam cross-section using just two resultants. One, shear force, which is a resultant of the vertical internal forces, and one bending moment, which is a resultant of the normal internal forces. This is a very common way of representing the internal forces within a beam. Drawing the shear force and bending moment diagrams is just figuring out what these internal forces are at each location along the beam. These resultant shear forces and bending moments will depend on the loads acting on the beam and the way in which the beam is supported. Beams can be loaded in a number of ways, the most common being concentrated forces, distributed forces, and concentrated moments. Beams can also be supported in a number of different ways. They can have pin supports, roller supports, or be fully fixed, which each restrain the beam in different ways. Pin supports prevent vertical and horizontal displacements, but allow rotation. Roller supports prevent vertical displacements, but allow horizontal displacement and rotation. Fixed supports prevent all displacements and rotation. If a certain degree of freedom is restrained at a support, we will have a corresponding reaction force or reaction moment at that location. For example, rotations are permitted for a pin support, so there is no reaction moment, but displacements in the vertical and horizontal directions are prevented, so we will have horizontal and vertical reaction forces. So how do you determine the shear forces and bending moments within a beam? There are three main steps we need to follow. First, we draw a free body diagram of the beam. This shows all of the applied and reaction loads acting on the beam. The next step is to calculate the magnitude of the reaction forces and reaction moments at all of the beam supports. We do this using the concept of equilibrium. To maintain equilibrium, all of the forces in the vertical and horizontal directions should cancel each other out. Similarly, all of the moments acting at every point along the beam should cancel each other out. This gives us a set of simple equations we can solve to calculate the reaction forces and moments. If we can calculate all of the reaction loads using the three equilibrium equations, the beam is said to be statically determinate. For some beam configurations, like this one shown here, we won't be able to calculate all of the reaction loads because we have too many unknowns and not enough equilibrium equations. In this case, the beam is said to be statically indeterminate. This beam has 4 reaction forces, but we only have 3 equilibrium equations. To solve this beam, we would need to use slightly more complicated methods and consider boundary conditions. In this video, I will only cover statically determinate cases, where we can use the equilibrium equations to calculate all of the reaction loads. Once we have calculated all of the reaction loads, the third and final step is to figure out the internal shear forces and bending moments at every location along the beam. To do this, we will use the concept of equilibrium again. If we cut our beam at any location, the internal forces and moments need to cancel out the external forces and moments so that equilibrium is maintained. This allows us to easily calculate the shear force and bending moment at each location along the beam. All we need to do is start from one side of the beam and move the location of the cut along the beam, calculating the shear forces and bending moments as we go. Now is a good time to define the sign convention we will be using. Applied forces will be positive if they are acting in the downwards direction. For shear forces and bending moments, the positive sign convention will be as shown here. If the beam is on the left side of our cut, shear forces pointing downwards will be positive. If the beam is on the right side of our cut, shear forces pointing upwards will be positive. Positive bending moments will be those that put the lower section of the beam into tension. Another way to think about it is that bending moments which cause sagging of the beam are positive, and those that cause hogging of the beam are negative. Let's take a look at an